Good morning. My name is Vilhjálmur Ásgeirsson, and the topic of my talk is methods for finding saddle points and minimum energy paths. The outline of my talk is as follows. I will start off by a brief discussion about potential energy surfaces, stationary points, and minimum energy paths. From there, I will move on to two classes of saddle point search methods, namely the single-ended and double-ended methods. These include the partition rational function optimization and also climbing a mid-NEB. I will conclude the talk by discussing a new method, a combination of both A and B that we call NEBGS. A potential energy surface describes how the energy of a molecule in a particular electronic state varies as the function of the molecular coordinates. Here you can see two-dimensional potential energy surfaces, namely the Leb's potential coupled with a harmonic oscillator as well as the Möller-Brown surface. Stationary points on the energy surface are points where the gradient of energy vanishes. These points are classified as energy minima, energy maxima, or first, second, and higher order saddle points. An energy minimum basin represents a stable state of the system. Surrounding an energy basin is an energy ridge, and on the ridge there are points of minimum energy that correspond to the first order saddle points. These points are maximum in energy along one degree of freedom, and at an energy minimum in all other degrees of freedom. In other words, the Hessian matrix at the first order saddle point has one and only one negative eigenvalue, and the corresponding eigenvector points along the reaction coordinate for a transition from one energy basin to another. By identifying first order saddle points, one can determine the reaction mechanism, estimate the activation energy, calculate the thermal rate constant, and identify a new energy minimum on the other side of the energy ridge. Moving on to minimum energy paths. Minimum energy paths are usually a good choice to represent the reaction coordinate, as the system moves from one minimum to another. These are paths for which the energy is at a minimum in all directions orthogonal to the path. On the Leb's potential energy surface, you see that we have three energy minima, M1, M2, and M3. They are connected through four minimum energy paths, which are shown here by these white dotted lines. There may often be multiple minimum energy paths that lie between and connect to energy minima. The maximum along a minimum energy path is a first order saddle point on the energy surface. Therefore, by identifying a minimum energy path connecting to minima, one obtains the corresponding first order saddle point as well. Okay, moving on to methods for locating first order saddle points. For the purpose of this talk, I'm only concerned with locating first order saddle points for a given reaction, and will discuss two different methodologies to do so, the single-ended methods and the double-ended methods. First is the single-ended methods, where the input is a single configuration, typically generated by interpolation methods, such as linear synchronous transit or constraint optimization. Single-ended methods tend to converge accurately to a first order saddle point, but the saddle point that they find is highly dependent on the initial guess. So what you need to do is you need to follow a steepest descent path down from the saddle point to the two energy minima. And single-ended methods use both first derivative and some information, usually about the second derivative of the energy function or the Hessian matrix. For the second class, the double-ended methods considered here, the input is the energy minima corresponding to the reactant and product configurations. The double-ended methods resolve the minimum energy path between the two energy minima by using a set of discretized images. And because of this, double-ended methods tend to require more computational time than the single-ended methods. However, keep in mind that the energy and gradient computations over the images can easily exploit parallel computing. And double-ended methods tend to use only the first derivative of the energy function. I will now give a brief review of the PRFO method. So PRFO is a single-ended method where the energy is locally approximated by a rational function approximation instead of by a quadratic approximation like in Newton-Raphson. The method works by selecting an eigenmode of the Hessian matrix that corresponds to the desired reaction coordinate. Note, however, that this mode has to be re-identified at each step in the optimization, as it is followed to a first order saddle point. This is because its position may shift in the eigenspectrum during the optimization. Okay, so to maximize the energy along the selected coordinate and to minimize the energy along all other coordinates, PRFO has to compute two shift parameters, the lambda path and the lambda reaction coordinate. These shift parameters are used to invert the gradient in the eigenvector basis given by gamma, such that the displacement made by PRFO is uphill in energy along the kth mode and downhill in energy along all other modes. Notice that PRFO requires the Hessian matrix to be computed and stored at each step of the optimization. However, as the computation of the Hessian matrix can be quite expensive and even computationally prohibitive for very large systems, the exact Hessian matrix is typically only computed at the first step in PRFO, or approximated by lower level of theory methods, such as semi-empirical methods, or by empirical estimates. During PRFO, one uses Hessian updates to avoid recomputing the Hessian after each step. And note that inaccurate updates may distort the eigenspectrum and make the algorithm lose track of the reaction coordinate, and therefore for difficult saddle points, it is often found necessary to compute the exact Hessians every few steps. For saddle point searches, the Hessian update scheme should not be forced to be positive definite, but rather allow for negative eigenvalues, and therefore you can use Hessian update schemes like the symmetric rank 1 or Powell symmetric Broyden. Bovill found that a linear combination of the two performed the best. And because of the use of two shift parameters and the tracking of the reaction coordinate between steps, PRFO can actually be initiated anywhere on the energy surface. You can start it from within the energy well, or even in regions with one or more negative eigenvalues of the Hessian matrix, and you still converge accurately to a first order saddle point. And in close proximity to the saddle point with an accurate estimate for the Hessian, PRFO may exhibit quadratic convergence properties. So what you see here on the left coupled to the harmonic oscillator potential, you see 9 PRFO optimization trajectories started from different position in the energy basin, and each one converges to a saddle point. So saddle point 1, 2, and 4. In this section of the talk, I will review the nudged elastic band method and its variant, clamping image nudged elastic band. These are double-ended methods that require the reactant and product energy minima as an input. A discretized initial path of system configurations connecting the two minima is generated. As you can see here, we have the reactant and we have the product, and we make a path by linear interpolation composed of 5 intermediate images connecting the two minima. Then the unit tangent to the path is approximated for each image by a line segment to the higher energy neighboring image. Using the tangent, we can include only the component of the atom force acting perpendicular to the path in the minimization. In other words, we move downhill in the perpendicular direction. To maintain the distribution of images during the optimization, spring forces acting along the path are introduced. The images are then iteratively and simultaneously shifted towards the minimum energy path according to a given gradient-based optimization method. Here you can see NAB optimization on the Möller-Brown surface after 25 steps. Already 3 images lie on the actual minimum energy path given by the red line. Notice that these 2 images might actually not converge directly onto the saddle point. Therefore, it is usually a good idea to convert the highest energy image along the path to a clamping image. This is done by transforming the effective force acting on this image such that it moves uphill in energy along the path and downhill in energy perpendicular to the path, like the other images. The climbing image is not affected by spring forces and tends to speed up convergence of the NAB to the minimum energy path. Also, if the main objective of your calculation is to identify the saddle point for a given transition, it may be a good idea to only gauge the atom force acting on the CI for convergence, or simply just employ weaker convergence thresholds for the other images. The spring forces are used to maintain the distribution of images along the path and ensure images do not leak down to the energy minima. In this talk, we consider 2 different types of springs, standard and energy-weighted spring forces. For the standard springs, all spring constants are chosen to be the same for each segment of the path, and an even distribution of images along the path is obtained. This may be useful if a high resolution of the entire minimum energy path is needed. However, for systems characterized by high degree of flexibility and minimum energy paths with long potential energy tails, such as for molecular reactions, it may be advantageous to use energy-weighted spring constants. In this scheme, the stiffness of the springs is scaled according to the energy in such a way that higher density of images is obtained in the barrier region along the path, as you can see here for the any reaction of 1-propylene and ethylene. The minimum energy path obtained by the standard CNF is shown by the gray line, where it's obvious that the energy barrier itself is poorly resolved. This often leads to oscillatory behavior of the CI and even unstable optimization. However, for energy-weighted springs, the resolution of the barrier region is excellent since the images get pushed uphill in energy along the path and toward the clamping image over the course of the optimization. Before moving on to show performance numbers of both standard CNF and energy-weighted CNF, I would like to address some issues that often arise in NEB calculations. In my experience, most problems in NEB arise from either insufficient number of images being used or simply poorly prepared reactant and product energy minima. So, preparation of reactant and product configurations, a few things to keep in mind. First, both the reactant and product should be at a potential energy minimum when you start the NEB calculation. Or for the more experienced user, you can use freehand NEB to optimize the endpoint images simultaneously with the others. Second, you need to make sure that the atom indices or the order of atoms in the .xyz configuration files are the same for the reactant and product. For example, see this isomerization reaction here. There is a one-to-one mapping of the ordering of atom indexes for the reactant and product configurations here, and you obtain the likely saddle point. To the right, I have swapped the placement of the two hydrogen atoms, and you get this crazy intermediate configuration with the carbon-carbon bond broken and the hydrogen atom flying off. And of course, this issue applies to any double-ended method. The third issue is to keep in mind to always superimpose and minimize the root mean square deviation between the reactant and product configuration before generating the initial path. As you can see in the example here, this will serve to remove trivial displacement along the path caused by the global rotation and translational degrees of freedom, and hence increase the resolution of the path where finite number of images are used. Another important issue to address is the initial path generation in clamping image nudged elastic band. As I stated earlier, before doing a nudged elastic band calculation, a finite set of images connecting the reactant and product minima need to be generated by some sort of interpolation. Typically, people have been using linear interpolation in Cartesian coordinates, which of course can well lead to highly unphysical intermediate images where the atoms may be overlapping. Also, such paths tend to be far from the actual minimum energy path. A much better option is to use the image-dependent pair potential method. It works by computing the distance between each pair of atoms in the reactant and product minima. Then a linear interpolation of ideal pair distances is made for the intermediate images, and an objective function for the deviation of the ideal and actual distances is minimized for each image using the NEB algorithm. A path generated by ITPP should not contain overlapping of atoms, and typically lies much closer to the actual minimum energy path than linear interpolation in Cartesian coordinates. Here you can see an example of the two interpolation methods, the linear interpolation and the ITPP, for a 120-degree methyl rotation. As you can see in the linear interpolation, the intermediate hydrogen atoms and the carbon atoms will be overlapping, while ITPP produces this circular motion, which is of course very close to the actual minimum energy path. And in these histograms here, you see a distribution of the maximum energy configuration along initial paths for linear interpolation and ITPP, made for a dataset of 120 molecular reactions. Obviously, the linear interpolation is generating highly unphysical intermediate configurations for some systems and should in general not be used. And also, remember always to inspect the initial path. This brings us to insertion of intermediate images. The clamping image nudged elastic band method is a local optimization method, and it converges to the minimum energy path, lying closest to the initial path. You can use insertion of intermediate images to the initial path to bring it closer to the minimum energy path and hence improve the efficiency of the calculation. You can also use insertion to locate different minimum energy paths that are otherwise not local to the initial path. For an example, by insertion of approximate saddle points, intermediate energy minima, or configurations guided by chemical intuition. Here, I have an example of hydrolysis of ethyl acetate, where the reaction can either proceed by a concerted single-step mechanism, or by a stepwise mechanism with two energy barriers. The concerted mechanism, shown here, is local to the initial path, generated by ITPP, while the stepwise mechanism is the more favorable one. We can obtain the stepwise mechanism by insertion of the intermediate energy minima, and of course, for the calculation we would like to increase the number of images for better resolution of the path. But then I would also like to use this chance to mention that in practice, if an intermediate energy minimum is found during a NEB optimization, it is often advantageous to partition the NEB calculation into two individual calculations, one going from the reactant to the relaxed intermediate energy minima, and the other from the relaxed intermediate energy minima to the product's energy minima. Before moving on to a discussion about the performance of standard and energy-weighted clamping image NEB, I would like to recall that in standard clamping image NEB, the same constant value for the spring constant is used for all line segments of the path, and this yields an even distribution of images along the path. While for energy-weighted clamping image NEB, the spring constants get adaptively scaled according to the energy of the images, such that the images tend to accumulate in higher energy regions of the path. So now I would like to show you some performance numbers and comparison of the two variants, where we have evaluated the performance for a large and diverged benchmark set of 121 main group molecular reactions, taken from recent work of both Paul Zimmermann and Birkholz and Schlegel. In these three histograms here, different properties of the benchmark set relevant to saddle point search methods are illustrated, namely the path lengths, the magnitude of the imaginary frequency at the saddle point, and also the barrier height along with the absolute potential energy difference of the reactant and product minima. We measured the efficiency for a set of clamping image NEB calculations by the average number of energy and gradient evaluations, shown by the red y-axis, and the standard deviation in the evaluation shown by the error bar. The success rate is shown by the blue y-axis and is measured by the fraction of clamping image NEB calculations that were successfully convergent. In other words, calculations where the atom force acting on the clamping image drops below the user-supplied convergence thresholds. You can see here that we did standard clamping image NEB calculations with a total number of images varying from 7 to 14 and using different spring constants, and the energy-weighted clamping image NEB calculations with 7 and 10 images. You can notice that by increasing the number of images from 7 to 14, the success rate of standard CNF increases from 74% to 93%, while already for 7 image energy-weighted clamping image NEB calculations, the success rate is 98%, and for the 10 image set, the success rate is found to be 100%. Also notice that the energy-weighted clamping image NEB variant is significantly more efficient than the standard variant, requiring only about 900 energy and gradient evaluations on average. That is 150 computational cycles or evaluations per image. The improved performance is attributed to the increased resolution of the energy barrier in the energy-weighted clamping image NEB variant, which leads, of course, to a better tangent estimate at the clamping image. In this section of the talk, I will introduce the new NEB-TS method. NEB-TS combines energy-weighted clamping image NEB with PRFO, which is also referred to as the TS search here, in an automatic fashion to efficiently and accurately locate saddle points for a given reaction. In NEB-TS, the energy-weighted clamping image NEB method is used to partially converge an initial path to an approximate minimum energy path, or more accurately, until the forces acting on clamping image drop below a user-supplied threshold, which I will refer to as the TS activation threshold. The location of the clamping image at the approximate minimum energy path is automatically taken and used to provide a high-quality starting configuration for the subsequent t-asserts. The initial Hessian matrix used in the PRFO or the t-asserts is constructed from the Almlof model Hessian, and the eigenmode overlapping with the clamping image tangent is selected to be the reaction coordinate, and the curvature of the mode scaled according to the curvature computed from the partially converged minimum energy path. In this manner, given that the TS activation threshold is properly selected, the PRFO or t-asserts is always started from a configuration close to the desired saddle point, and the computation of the initial exact Hessian matrix is not needed. Here is an illustration of the NEP-TS optimization for the Muller-Brown surface. You can see that we start from an initial path composed of 10 images connecting the reactant and product energy minima. From this path, the CNF method is used to partially converge to the minimum energy path, and the clamping image configuration is used to initiate the t-asserts, which goes directly to the exact saddle point. And in this figure, we show the energy barrier as a function of optimization step for the concerted hydrolysis of ethyl acetate. The results from standard clamping image NEB calculations using both 8 and 12 images, energy-weighted clamping image NEB calculations using 8 images, and NEP-TS calculations using 8 images. It's really evident how the convergence behavior of the calculations improves as you move down the plot. I would also like to mention that in NEP-TS calculations, all CPUs that were previously used to parallelize the clamping image NEB calculations are redirected to parallelize the electronic structure computations in the t-asserts. Using the same test set as before for the clamping image NEB calculations of 121 main group molecular reactions, we evaluated the performance of the NEP-TS method with different values for the TS activation threshold. The efficiency for a set of NEP-TS calculations is measured by the average number of the total energy and gradient evaluations required for the TS to converge and is shown by the red y-axis. Standard deviation of evaluations is shown by the error bar here. The success rate of NEP-TS is measured by the fraction of convergent calculations and shown by the blue y-axis. That is, NEP-TS calculations where the atom force acting on the TS image drop below the user-supplied convergence thresholds. According to this criterion, however, a calculation that converges to an incorrect or a bad saddle point is still counted as a success. I will discuss this in a moment as well. The dashed red lines with diamond markers show the number of gradient evaluations used in the initial energy-weighted CNF, and the red dashed line with square markers show how many gradient evaluations are needed in the subsequent t-asserts of NEP-TS. Obviously, most of the computational effort is spent in the NEB part of the NEP-TS method. So, we ran 3 variants of the NEP-TS method on the test set. First is the ITPP-TS method, where the t-asserts is started from the highest energy image along an ITPP initial path, and then 2 sets of NEP-TS calculations with a TS activation threshold of 0.01 and 0.02 Hartree per Bohr. NEP-TS with a TS activation threshold of 0.01 Hartree per Bohr yields a 100% success rate and an impressive average of 305 energy and gradient evaluations. This is roughly 1/3 of the evaluations compared to full energy-weighted clamping image NEB. However, interestingly, 5% of the successful calculations yield a large energy deviation, or a deviation larger than 2.5 kcal per mole from a reference set of saddle points that we created. And there are at least 3 possible explanations for large energy deviations with a saddle point obtained by NEP-TS from the reference set. First is that NEP-TS converges to a different saddle point than the reference saddle point along a multiple extrema minimum energy path, and this is of course to be expected for some cases. Second is that NEP-TS converges to a different saddle point than the reference saddle point on a different minimum energy path, but this is still a minimum energy path that connects the same reactant and product state, and this is fine. Third is that the NEP-TS can converge to a different saddle point on a different minimum energy path, which does not connect to either the reactant and or product state. this would be considered an incorrect saddle point. After a careful analysis of the calculations that showed large deviation, we found that only 3 of the calculations lead to an incorrect saddle point. And these calculations get fixed by lowering the TS activation threshold even further. But as you can see here, this also increases, of course, the average number of gradient evaluations as more time is spent in the energy-weighted clamping image NEB. Before moving on, I would like to just say that IDPP TS is behaving remarkably well with a success rate of 97%, and only 15% of the obtained saddle points show large deviation from the reference set. Compared to a TS where it started from linear interpolation in Cartesian coordinates, which has about a 70% success rate, from which 40% of the obtained saddle points exhibit really large deviations, up to about roughly 100 kcal per mole from the reference saddle points. And I would attribute the success of IDPP TS to the quality of the IDPP initial path and also to the robustness of the PRFO method for converging to first-order saddle points. So, to summarize what we've discussed so far, a first-order saddle point on an energy surface can be used to characterize the transition or reaction between 2 states, the reactant and product states. To identify such saddle points, the clamping image NEB and the PRFO method, or the combination of the 2, can be used. PRFO is a single-ended method. It can be started anywhere on the potential energy surface. It makes a rational function approximation to the energy surface. It uses shift parameters to ensure that the energy is maximized along the selected reaction coordinate and minimized along all other degrees of freedom. It uses second updates of the Hessian matrix to avoid recomputing the Hessian matrix in every step, and eigenvector following to track the reaction coordinate between steps. Bear in mind that the saddle point obtained by PRFO is highly dependent on the initial configuration and the choice of the reaction coordinate. Clamping image NEB is a double-ended method. It identifies the minimum energy path connecting the given reactant and product energy minimum, and hence the desired first-order saddle point. The path is represented by a set of system images. Force projections are used to minimize the atom force on the images acting perpendicular to the path. Spring forces are used to maintain an even distribution of images along the path during the optimization. Clamping image is used to converge accurately to the highest energy maxima along a minimum energy path, that is, a first-order saddle point on the energy surface. Energy-weighted CNEB adaptively scales the spring forces during the optimization to yield a higher density of images in the higher energy regions along the path. This drastically improves the efficiency and robustness of the method compared to the clamping image NEB in applications to systems characterized by high flexibility. Then NEB-TS combines the energy-weighted CNEB and the PRFO method in a highly reliable and efficient method for locating a first-order saddle point for a given transition. So finally, I want to briefly review a few important input parameters for clamping image NEB and NEB-TS calculations in ORCA. Here we have an example of a very simple ORCA input file for clamping image NEB job. In the simple input line here, you can either instruct ORCA to do a CNEB calculation or a NEB-TS calculation. Then for NEB specific input commands, you have to open up a NEB block. Here, the NEB and XYZ file instructs ORCA to find and read the product energy minima configuration. The command nimages informs ORCA how many intermediate images should there be used in the calculation. And the CNEB implementation is highly parallel, where the energy and gradient computations of the movable images can be calculated in a near-perfect parallel manner for every computational cycle, where you can parallelize both over the image calculations and the individual electronic structure computations. Then we end the block, and then we specify the reactant energy minima here in the normal coordinate section of the input. Here I've added some useful input commands into the NEB block. NEB-TS XYZ file allows you to insert images into the initial path generation. NEB-restart XYZ file allows you to start from a pre-made path or restart from a previous calculation. Energy-weighted boolean allows you to turn on and off the energy-weighted variant. Spring const is the spring constant for CNEB calculations and the lower bound of the spring constant for energy-weighted CNEB calculation. Spring const 2 is the upper bound of the spring constant for energy-weighted CI and F calculations. Tall turn on CI is a force threshold and instructs ORCA when to turn on the clamping image variant of NEB. Tall max FCI and tall RMS FCI are the convergence thresholds for the CI NEB and also for when to initiate a TS search in a NEB TS job. Tall scale determines the convergence thresholds for the other non-clamping images of the CI NEB job. The convergence thresholds for these images get set as the threshold for the clamping image multiplied by the tall scale parameter. Conf type instructs the NB code whether to monitor the CI for convergence or all of the images. Interpolation tells the NB code what kind of initial path generation should NB start from. The opt method is of course the optimization method. Max iter is the total number of allowed iterations. Max move is a simple trust radius. If the maximum absolute component of a step exceeds this radius, the whole step will get scaled down. And then a very useful parameter is the LBFGS restart on max move. This will instruct the LBFGS optimizer to reset the memory if a step exceeds the trust region. Okay, I would like to thank my professor Hannes Jónsson and all of my collaborators, Kristoffer Riplinger, Benedikt Orri Birgisson, Ragnar Björnsson, Frank Nesse, Ute Becker, and Frank Velmos.